Share. Screen share. And I'll do my entire screen. Share. Get a massive feedback. Ooh, that's always fun. Okay, so view the web. Okay, here we go. Oh, this full delayed. Ooh, that's the cool part. Okay. Is it down sampling?
Is it the internet?
Up. Of course.
It's not HD streaming.
Oh wow.
You can see the link actually works. Yeah, let's see how it looks like. Okay, so this is pretty clean here on this. I think it finds it.
So we should only be watching it one place. But yes, that means fine to check it.
Let's check it.
Hmm?
Is this normal?
Sometimes it started. But it should.
Why isn't your audio?
Oh, good question. Do you have the audio on? I do.
It's not coming in. My speaker is on fine. So it's 9.
Okay.
25 people are watching.
Hello, everybody. We're getting ready to get started.
It's not coming.
So no sound.
No sound. Yeah.
It's weird. Maybe muted somewhere in the Hangout itself.
Hello, can people hear me? Oh, is it this thing? Is this on mute?
No, the sound goes well. So we have feed, but we don't hear anybody because it's one way, I guess.
Can hear you loud and clear.
Okay, super. Okay, we got
Okay. Are we hearing ourselves? Okay. And I think we're ready to get going.
Yes.
It's close to me. Okay. Yeah, perfect. It's good to open.
Okay. Good morning, everyone. Sorry for a few technical glitches. This is Planet OS's first webinar, and we're still shaking things down. Please, if you have any problems hearing what we're doing or technical difficulties, or you have questions about the content, up here is Twitter places you can put it. We'll be monitoring that, and you can put things in the YouTube live chat channel too. So anywhere you want to put either problems or questions, please feel free. We'd love to be more interactive today. So with that, let's get started. I'm here with Dr. Sangram Ganguly, my good friend, who's at NASA Ames and Bay Area Environmental Research. And we want to talk today about work that Planet OS has done based on the work that NASA has done to make climate models really easy to use with people. Hopefully by the end of today's webinar, everyone who's on here is going to be able to use the climate model data themselves to look at various places or questions of interest regarding our climate future and understand what scientists around the world have said about your hometown or your country or some area that you're interested in. So we're going to walk you through the tools and how to use them, and they're not very hard to use, which is nice, and they're pretty quick. So at the end, I think you're going to be in good shape. So I'm going to turn this over to Sangram to give you an overview of what OpenNext is and NASA's initiative there. And then after that, we'll go straight into demos and a little bit of education about how to use it. So Sangram, let me get your PowerPoint up so people can see your slides.
All right, thanks, Tom. And I won't take much of your time here. Just to introduce you, I've been working with Tom and the whole team here at Planet OS for almost 2 years now. What essentially, Planet OS approached us, and they wanted to do something with the data that we are producing on a day-to-day basis. And on the climate side of it, we have been doing a lot of different kind of stuff. And I wanted to give a brief overview on what essentially NASA Earth Exchange is all about. And so, traditionally, science, as we see it from a researcher's perspective, we always tend to download data in our laptops and then start analyzing that data and produce some good science out of it. But that model is slowly disappearing. I mean, data is getting bigger, the volume of the data, and should I hold on? I think the slides are not up there.
We're all good.
Oh, okay, we're all good. Okay, perfect.
Sorry to the audience. We're experimenting with our first webinar here, so there may be a few more technical glitches like that. Again, let us know if you're having trouble out there, and we'll be monitoring that.
Yeah. In the chat, right? Sure.
In the chat or in Twitter.
Yeah. So the whole vision about NASA Earth Exchange was to provide science as a service to the Earth science community, addressing global environmental challenges. And the goal is to improve efficiency and expand the scope of NASA Earth Science Technology Research and Applications Program. And so NASA Earth Exchange is almost like a virtual collaborative that brings scientists and researchers onto a single platform to engage and enable science as we know it today. So what we have been trying to do over the last 5 years, and since the inception of NASA Earth Exchange, is to bring in all kinds of data related to Earth science. And we're talking about satellite data, climate data, different kinds of climate models, a lot of ecoclimatic models, physiological models, and all of them are centralized in our NASA Advanced Supercomputing division. So in addition to data sets, we are also creating different scientific workflows. So for example, I publish a paper somewhere, and there is a workflow associated with it. Researchers are now able to replicate that whole workflow using the tools, the codes, and the data needed to do that. So we call it science as a service. So we have ready-to-use data, ready-to-use models, access to workflows, virtual machines. We are getting there. NASA is slowly adopting the whole whole Docker model, and then right now what we're having internally inside of NASA is more towards traditional workflows where you have scripts essentially tagged to one another, right? We have a web portal where you can actually go and visit all the projects for the NASA Earth Exchange. There are different principal investigators. The project registration is open to everyone. And if you want to use the NASA Earth Exchange facility inside of the supercomputing division, it's currently for all the NASA-funded principal investigators and teams. So if you're funded under any of NASA grants, you can actually get full access to the whole supercomputing division. So I wanted to give a brief overview on how we are organized. So we have the whole nice NEX, NASA Earth Exchange Science and Applications box, and we have a NEX software platform, and we have the NEX infrastructure. So the compute infrastructure is the Pleiades supercomputing architecture inside of the NASA supercomputing division, and it has almost we have access to almost right now almost 150,000 cores on doing dedicated processing. We have almost we are almost hitting the 2 petabyte limit on the data storage. We are getting a lot of the satellite data, especially the Landsat data, takes a lot of space. We have a collaboration portal and a knowledge base, and I'll talk about later a little bit on our initiative with Amazon for the last 2 years on transporting this whole NEX environment onto the cloud. And The next layer, what we call, is the next software platform. So we have a science data management, we have workflow and process management, we have knowledge management, and we are heavily into outreach and engagement. And that's where this led us to the collaboration with Planet OS. Some of the next science and applications were heavily concentrated on global science products, essentially creating global products from Landsat, MODIS, and these are heavy-duty processing. Processing global Landsat data almost requires, and we are almost creating almost monthly mosaics of global Landsat surface reflectance. We have several funded projects from NASA, specifically focusing on carbon monitoring. And on the application side of it, we have water management as a key focus area. The climate, which I'll be talking about next in a few slides, is again another key focus area which we have been trying to help the National Climate Assessment. The land cover is a very specific focus area. Since the last 2 years, we have been looking into scalable machine learning algorithms to do automated object detection and classification from very high resolution satellite and airborne imagery. So machine learning is also a very key focus. Some examples on what kind of data we have. Although we write here greater than 800 terabyte, but we are actually hitting the 2.3 petabyte storage with all the satellite data sets and the climate data sets. I won't go into the details here, but this kind of gives you a brief snapshot of what kind of things we are having inside of NEX environment. So as I was talking before, we are all about scaling it up. So deployment on the NASA supercomputing resources, and then essentially taking it to the next level where we can actually migrate the whole thing onto the cloud. Here I want to kind of finish my introduction on how we are supporting the National Climate Assessment. And this is a very important project we have. We have collaborators on NEX who are actually creating this very high resolution downscale climate projections data sets. And it's extremely important for modeling impacts, for doing long-term satellite data analysis, for a lot of climate modelers, for a lot of eco-physiological modelers. And we are always trying to create this very high resolution, robust climate downscale data sets with less uncertainties. And to that regard, this kind of gives you a brief idea of how these data sets look like. We have almost 35 CIMIC 5 models, and I'm sure Tom has some details on that. He can give you more information. And the spatial resolution is at 800 meter for the continental US downscale climate projections data sets, and we also have a global downscale climate projections data set. From here on, I just wanted to show how our open NASA Earth Exchange initiative looks like. And I think I could directly go into the website just to give a brief overview, Tom. So just. Right, so this is kind of our philosophy behind OpenNEX. It's discovery, access, and analysis of NASA Earth Exchange data in support of the National Climate Assessment. So as you probably know that we are working with a number of teams, and we really like this idea about companies and teams coming together and creating these beautiful tools to analyze and climate data sets and do some real core science out of it. So we have partitioned this whole OpenNEX effort into what we call knowledge, where we have previous videos on some of the NEX supercomputing workshop. We had a 2014 OpenNEX workshop. So there are some videos which might be very interesting to a lot of you in the audience. We have a 2016 OpenNEX videos, although it didn't start yet. We are populating with some of the new videos which we're creating on some of the interesting topics. Here we have journal articles which have been using NEX data. We are populating this list too. This will also be very interesting for a lot of stakeholders and policymakers. Data is essentially the key data sets that we are creating inside of NEX. And I think Tom will be discussing more on the NEX DCP30 and NEX GDDP, which is the global downscale dataset, and the continental US downscale datasets. We have also recently launched a new dataset, the LOCA dataset. Access, we have different ways of accessing these datasets. We have partnership with Amazon Web Services, where they're willing to host everything on the public cloud, and I'm sorry, the public datasets program, and it's all free. You can download these datasets. In fact, Tom is going to show you a lot of those details here. NCCS also hosts the datasets. We are slowly migrating a lot of them into the Microsoft Azure cloud. Google Cloud already has the next DCP30 data. So all that information and how to access these data sets are all provided here in the OpenMX portal. Some of the applications, this is exactly where our partners and collaborators come in. We have been working with a lot of different teams here. We have our own research team inside where we do essentially write science papers, not fancy stuff like you guys do in Planet OS, but that's how it's been done in the research community. So it's very interesting to see how companies like you actually make this go broad in the public and make it easier for people to use these data sets and do something interesting out of it. I think that is the key. So I won't go into the details. I would let the users go into the portal and see what all we have. But we definitely highlighted Planet OS application right here. And I think I'll hand it over to Tom.
Great.
Thank you.
So I didn't introduce myself at the beginning, of course, failing that. So first lesson of webinars, but thanks, Sangram, for giving us that great overview. I'm Tom Fallhaber. I'm the guy, along with Ilya Kamushkin, who's here with me, who built this tool that we're about to talk about today. And let's dive in. I want to show everyone here how to use climate data in a way that's accessible not only to people who write complicated computational fluid dynamic codes, but I want to show how, you know, a data journalist or a researcher or a student who's interested in understanding the data, or, you know, we're also interested in making this climate data usable by people who are looking at risk assessment, for example, people in insurance. So we envision a wide variety of users of this, and hopefully we've made it accessible enough that you can use it. So when let's open the Planet OS application here. When we first were talking to Sangram, the sort of mutual realization we had is that having this open data in Amazon S3 was fabulous. People could get it, people could use it, but it was still hard to use for regular people using regular tools. You had to learn a lot, you had to learn special formats. It took a long time to download the data. The files are about 2 gig a piece, and you tend to have to download a lot of them. And so what we wanted to do was come up with a system where it was very easy for people to build their own data sets that are subsets of the overall data that's available and targeted at what they're doing, and then use that data in tools they're familiar with. So I'm going to walk you through 3 examples of how to use data, and I'm hoping by the end of that you'll see how to use the data you want to use to get it, and to do your projects, or maybe set up projects for classroom or collaborators or all sorts of things like that. The possibilities are pretty endless for people who want to explore the climate. Now let me overview these 2 data sets and the CMIP5 initiative that they come from. So there, as Sangram mentioned, there are 2 data sets that are climate projective data sets. And I'm going to dive into one, which is GDP here, so we can look at it. And here we have data. The data comes from a variety of institutions around the world having built models, and we see different, here we have one from Australia, from China, various ones from like the NSF and NCAR in the United States, France, Japan, a bunch from NOAA, Germany, Norway. So different institutions around the world who are doing climate modeling themselves. Under CMIP5, they've run their models under a standard set of scenarios. There are 4 scenarios here 2 for the global set. We've recorded 2 for the global set, and we'll see in a minute there are 4 for the local set, about what carbon emissions and land use will look like over the next century. The range of the data set is we have a retrospective run from 1950 to 2005, which is like, what would happen if we ran the model against those years? Does it tell us something that's actually kind of consistent with what really happened? That's a good historical test for the model. And then future projections through 2100 under the different scenarios. And we can combine these. And we've measured 3 variables: precipitation, max temperature, min temperature. Now, the GDDP data is global quarter-degree data, which is modeled daily, so across this quarter-degree grid all across the globe. And so let's use an example of this. I want to show you how easy this is to use. I'm going to start, throughout this, I'm going to use a particular model I happen to like, which is NOAA Geophysical Fluid Dynamics laboratory model. That's a pretty sophisticated model, but you can explore the models. You can follow the links in the documentation that tell you the different institutions, and can go to their particular write-ups about what their model was and what they were trying to do. So I'm going to look at, I want to look at 5 years of history of this model for this example. And we can just pick the years we want, and I'm going to pick from the beginning of this year through the end of 2020, and look at max temperature. Now I want to look, and I'm just going to pick one scenario, and this close in the future, the differences between the scenarios typically aren't very big. Let's select an area here. So I'm going to go, there's an area in Chicago that I always like to use, and there are 2 reasons I like to use it. One is it's the center of Ray and Charles Eames' book, Powers of 10, which everyone interested in science should read and share with their kids, because it's an amazing book and an amazing film from a long time ago. So let's find, oops, now I lost Chicago. Here we go. So I'm going to pick the field, basically, that they use at the center of the universe in that book. And you see here we can navigate just like we were on Google Maps or something. We navigate around and we zoom in, and now I see down by Soldier Field in Chicago. We can just, oops, don't want to do that yet. We can just select an area here. Let's just select this little area around Soldier Field, which is where the participants in that book are having their picnic back in the 60s. But so now we see we've picked a rectangle, we've picked all, or picked a polygon, we've picked all the things. In this data set, that polygon's a lot smaller than 1/4 of a degree. So even though I drew a little bit complicated polygon, it's really going to be 1 square in our grid. And there's a reason I did that you'll see in a minute. And now we've picked a model. We could pick multiple models and compare them. I don't want to do that in this example. We've picked a range of time. We could have gone all through the range of the history or any subset. And we picked a variable. Again, we could pick multiple variables. Same with the scenario, which is the scenario we ran the model on. So now let's create a new data set. And this actually creates, it's very fast because all it did was create a specification for the data set. We can, this is a very small area, so we can download this directly from the server, and that's what we're going to do in this case. I'll talk about the other cases later. So let me just, instead of downloading a file straight away, I'm just going to copy the link for that. And now, just to show you, oops, that's not what I meant to do. Just to show you how easy this really is. Hello. I'm going to actually open this in Excel. Sorry, we had a little glitch there. I'm going to open this in Excel. So there's no, Excel is not a tool we really use for climate, but it is actually an interesting tool that a lot of people do use. Oops. And I'm going to open that URL directly in Excel. And that's just the URL that it gave me to download directly from the server. We've downloaded it, and now we can see, let me zoom in on that so it's easier for people to look at. We see we have a bunch of columns, and the data we got is just comma-separated value data. This tool can deliver either comma-separated value data, which is very easy for lots of tools to deal with, or data in a format called netcdf, which gives you multi-dimensional arrays, and sometimes when you're dealing with larger chunks of data, is a little bit easier for your program to deal with. I'm going to work all with CSV data today. But if you look in the documentation, you'll see examples of how to work with netcdf for larger quantities of data. So we see here we have a bunch of columns. We have the data, and you see this is every day starting this year in 16. We have the long lat of the center of the square. We see we only had one square here. I did that on purpose so the Excel munging would be easy. We'll do some more complicated examples in a minute. We see the model. Again, we only picked one model and one scenario and one variable, so they're all the same. And then we see the value. That looks kind of hot for Chicago, for max temperature. I've been on hot days in Chicago, and it's usually not that hot. In fact, the reason it's that way is because NASA likes to do things in degrees Kelvin because they launch space probes. I'm going to actually use my Excel skills and turn Kelvin first into Celsius by subtracting 273.15, like we all learned in physics class. And then because I'm an American and off the world standard, I'm going to convert it to Fahrenheit, like that, like I learned in elementary school. And that is 30 degrees in January, a high in January, which looks a little more normal for Chicago, which actually gets down to 10 degrees and so on as the daily high for these days in this model. So that's interesting. Those temperatures look believable. If I scroll down here, I see in July it's 87. That seems right for Chicago. So so we can easily work with the data in Excel just like this. But really what I want to see is what it tells me about temperature. Let me select these two columns. It's Excel. One of Excel's great things is easy charting. And voila. So I picked 5 years of data. Let me delete that because we know it's temperature. And let's make this big so it's easy to see. And what we see over 5 years is Chicago is really cold in the winter and really warm in the summer. So that's the second reason. I said there were 2 reasons I picked Chicago. The differences between winter and summer in Chicago are among the biggest in the world, maybe. So we see in the summer it gets up to about 100 degrees Fahrenheit, high 30s Celsius, and in the winter the highs are down between 20 and 40 degrees Fahrenheit. So this is sort of how we collect the data. This is 5 years, of course, is too short a period to do real climate science. We'll talk about more climate science stuff later, but we can see how easily we could pull the data out and do it. We could have done 100 years of data, and we could do more advanced statistical analysis. Pretty soon we run out of what's easy to do in Excel, of course, but you can do a lot in Excel if you know Excel pretty well, and we see here that we can directly load the data into Excel. But now let's look at a different example. And really, if you have any questions, put them in the chat. Ilya will kick me if you do. If we have questions that we should be answering going along, and I'll interrupt what I'm doing to do questions. And that document was so easy to make, I'm not even going to save it. So now, let me do a different example. And what I want to do is look at an area here in Northern California where we're based. We're here in the office in Palo Alto, so I'm going to do an area around this. And I want to actually, well, I'll just open it here. I was going to drag and drop it from my desk. So a lot of times when we're doing data, we might want a very complicated region. For example, I want county boundaries or state boundaries or province boundaries or country boundaries. And it's hard to draw that with a polygon accurately. But a lot of times we have the information in a file from our GIS system or something else. And this system supports uploading that. We can upload shape files, KML files from Google Earth, or GeoJSON. I'm going to upload a shape file here. And I'm going to get it off my desktop. I can find my desktop. Here's my desktop. There it is. And I have a county called 4counties.shape. a file called 4counties.shape, and we see here it just loads in, and you can see the boundaries of San Francisco, San Mateo, Alameda, and Contra Costa counties in the Bay Area here in California, and we get that. So I want to look at that. I'm going to use the same model here, but I'm only going to take 1 year's worth of data here, and we'll take max temperature again. Oh, except I lied. I want to use the really fine-grained next DCP30 data. This is, as Sangram mentioned, this gives us data refined to 800-meter resolution, which for modeling 100 years of climate is pretty precise. So I'll pick the same model, and let's pick the range just being this year from January to December, and let's see what this model tells us about my 4 counties. So I'm going to pick max temperature. I'll pick the same scenario here. So let's upload that shapefile again. There we go. Okay, so now we see this. We see these 4 counties. Now we'll get high resolution data. This will be nice. And we see that actually had the polygons for the 4 counties, and they're complicated polygons. Now this is too big an area for the server to do it for you. And part of the goal of this project is to let people do their own custom transformations without having to get accounts and without having to pay money or do anything else to support the project. So we want everything to be free for everyone. So what we do is we use the Docker tool, which is a tool for deploying software and running containers. We have more documentation and pointers to really deep documentation in the documentation on the site. But basically, this means you can run this anywhere. And I'm going to copy this command. There's a simple command you run that gives you, that lets you run the exact Docker container on your own machine. So I'm just going to run this in my shell here by just copying that in. And now we can see that I'm just running a command, and it runs it in bash, and we will run that locally here. So it's downloading the command from our website at opennext.planetos.com and starting a Docker container and doing all this. Hopefully we'll be lucky and this will work. So now it's starting up. Yep, there we go. So now it's giving us information about what's in that container. We see the data set, which is what we picked, the model, the scenario, the variable, and the time range is around this year, and then the regions. So that's good. So now we have a server that's our custom server that we just built that will serve this data. Now, when I'm doing analysis, I mostly use a tool called R, and I'm going to show you an example in R of how we use this data. So let's go here. I've got R running over here, and I've got my little program to do this. Let's actually make this a little bigger so it's easy for people to see. So we have the commands here. Oops. Wrong file. Now, one sec, let me pick the actual right file. There we go. We have the commands here. I have them in an R Markdown file, but I'm going to run them in the commands. We use 2 R libraries. These are famous libraries for everyone who uses R. I think you'll know what they are, but they basically do our data handling and our graphing for us. So let's just load these. And we load those. And then we have a function to load the data. And this function is really easy. It basically does a read CSV straight out of the local container that I just started running. We start the container, and it listens on port 7645. And if you want to use this in R, you can just copy this, and it will connect to your container and get your data. You run a new container whenever you pick new data, and everything's easy. We specify that the date column is actually a date, so we can use all of our date manipulation on that column. And then we do the same thing that I did in an Excel to convert the temperature from Kelvin to either Celsius or Fahrenheit. And you can, by default, it does Celsius, but you can specify Fahrenheit. So let's load this function. And we do that. And now we just call that function to load the data. And we call it pointing at localhost because I'm running the container here. A lot of times you might want to run the container in EC2. And I'm going to show that because that's closer to where the data actually lives in S3. I'll show that in a minute. But now let's look at this. And this will take a minute to load. I can see it pulling in data pretty fast. I don't know exactly how long it will take because I haven't run on this network. But now it's loading the data from that instance. That instance is going out and reaching out to S3 and loading files from all the files that we referred to from S3. We never had to worry about which files they were, and loading them here. And it took about 20 seconds to pick exactly our data. Now let's see what's actually in that. So how many rows did we get there? Which is the same as how many points because it's CSV data. So let's take that and we'll do that. Oh, we have 97,000 rows for the grid for this 1 year. That's 1 point per month for every grid point. And let's actually get a summary of that so we can see the data. I'm going to pull this up so we can see the summary a little better.
That's for all the 3 shapefiles, right?
That's for the 4, yes, Sangram, that's for the 4 shapefiles for the 4 counties that we had. They all come back in a single file. So one of the nice things about this tool is you can pick multiple sources, but they get combined into one thing, so you can work in them in your analytics tool together. For example, if we picked more models, we picked one model here, but if we wanted to compare maybe 3 or 4 models under the different scenarios, what do the Japanese institutes say versus what do the European institutes say, for instance, we could put those into the same file, and then we could use tools in we'd probably use dplyr to disambiguate that and compare them. And then we could use ggplot to do comparison things, and similar tools in Python with Python pandas. I'll show you that in a minute, some of the Python examples. But here we see we have dates, ranging across this year. And then we have a grid. We see we don't have the same longitude and latitude. We have multiple grid points now. We have a single scenario. And then down here we have a single variable. But we have a range of values. That's the Kelvin temperature. And we see that Northern California doesn't get as cold as Chicago. 51 degrees Fahrenheit is our minimum temperature. And yeah, and here's our variable. That's the maximum temperature that we have, and we have 97,000 instances of that one variable. Again, we could pick multiple variables. You might want to, show the monthly average high and low temperatures, for instance, or you might want precipitation included in your data set. You pick and choose in the web interface, and the data, you get a single data set that contains everything and lets you disambiguate between them. So that's that. But that's nice, but it hasn't told us a lot. So we can also look at some of what's in the fields. I'm going to make this part bigger at the cost of our code. We can see different fields in here and get the unique values, and that's sometimes interesting for understanding the structure of our data. But really, I want to understand things like, so where was the coldest point? Oh, it was 51 degrees. We already knew that from the min and max. It was at this lat long point. And it was in December, which makes sense. December is a cold month. And where was the warmest point? Oh, it was in July at this lat long point. Now, right about now, when I'm doing this, I begin to wonder, well, where's that lat long point? Am I going to go into some mapping tool and find it, or do something else? What I really want to do is see all this on map. So we're going to use a tool called ggmap, which is part of the R graphing library. And I just wrote a couple of functions here. Let me actually walk through them a little bit. To do the maps, we find the bounding box of our data. That's pretty easy. It's just the min and max, longitude and latitude, creates a bounding box, and we give it a little padding so we don't run off the edge. And then we do a wrapping with that bounding box. We get map data. This is all documented in the ggmap stuff in the R documentation. And then we can do, and so our programmers will probably already know how to do this. And then we take ggmap and we put the raster of the grid on it that we want, and we interpolate so we get nice, smooth, pretty pictures. And then we set the fill to be based on we see we have the longitude and latitude creates a grid, and the temperature is the fill. And we set some transparency so you can see through to the map underneath. So let's do that, and then I want to grid it by month so I can compare the months. So let's try that. I did actually already run that. Okay. So then it's pretty simple. Once we have that function, it's really easy just to run that on our data. Just run map VF by month, which is the function we just defined. It downloads the tiles for the map itself, and it's doing that and grinding away on the map. This takes a little bit of time to figure out the whole map, and then even more time to draw it after it says it's done. It's not really quite done. This is where we have to have a little bit of patience. That's not a very useful picture. Let's zoom in on that. So now what we see is we see the monthly average high temperature for each month for these 4 counties. And what we can see is in the winter in San Francisco, there's not much variation. There's also low temperature. It gets, as with most places in the northern hemisphere, it gets warmer as summer comes. But what's interesting about the Bay Area, as those of you who spent time here know, is by the water it stays very cool even in the summer. We can see here in July in San Francisco it's cool, and in inland it's warmer. Now the range here is determined, the temperature range is determined by the whole year. So in January we don't see much variation because every area is at the low end of the range because we're graphing the whole year at once. Similarly with December. This summer there's actually a lot of variation, so we see more of that. But let's look specifically at December and July, which are the coldest and warmest months respectively. And we can get a better picture of what's happening. So I did something. I can just use subset and select out a month. And I'm going to start by selecting the coldest month. And now we've loaded all the map tiles, so all we have to do is draw the map. And now we can see in December, which is the coldest month, actually places by the coast are the warmest because they're warmed by the Pacific Ocean. And as you get inland, it actually gets cooler. And we see over in this southeastern part, that's near like Mount Hamilton and some of the other areas in the mountains that separate Silicon Valley from the area just to the east of it, that we see it actually gets to be pretty cool temperatures. So this is what winter looks like in the Bay Area, warmer by the ocean and cooler inland. Now let's look at summer. And again, we just subset to July and use the same function we already had. Let's do that. And we see in summer, we get just the reverse picture. The ocean keeps the coast cool. These are the blue temperatures now in the cool. Now the scale has changed a lot, right? We see now the low is in the 70 degrees Fahrenheit and the high is 100 degrees, so it's summer. In fact, the temperature by the coast, which was red before, is warmer than the blue that it was cooler than the blue we see here, because it's all relative to what July's temperatures are. We've rescaled the data. But we see it's cool by the ocean and very warm, and anyone who's been to Livermore Labs or somewhere like that knows how warm it gets out there in the summer, and it's 100 degrees Fahrenheit every day. So that's an overview of how to use R to get this data. I think those of you who know R will now know tons of ways to look at your data using ggplot or baseplot or other tools. I wanted to show ggmap because that's interesting to me, and I end up using that a lot as a way to understand what the data in my grid looks like. And so yeah, that's using R. Now, R is just one tool you can use. The data is pretty standard. So my next example, I'm going to switch gears. I'm actually going to quit R here because we're done with R for right now. Yeah, okay. So now what I'm going to do is I'm going to show you a couple of different things. The first thing I want to show you, and this data is going to be from Calcutta, India. And you saw it was a little bit painful for me to navigate on the map before, and I also want to make sure that every time I do the example, it's kind of the same thing. So let's switch gears. And one of the great things about this tool is when I make a selection, the system saves a permanent link to that selection. And you can do whatever you want with those links. And you can, for example, bookmark them, which I did here. I use a bookmarking service called Pinboard, but you can bookmark them on your local machine or in a service you use. And it will go straight to that selection in that data set. So you see here I've put a polygon around Calcutta that does this. And you can get this when you make a selection, it changes your URL, so you can just bookmark it straight away. But you can also select it from over here on the side. You see I have my selection here, and when I do that, I can copy that. I can send it to a colleague. I can put it in a blog post or a paper that I'm writing. So all of a sudden, everybody can use the same data, the exact same model run data, including the geographical constraints, the selection of time and scenarios, and everything else that I've used. Now, the examples we've done to date, the first two examples were cool and they looked nice, but they didn't tell us anything about long-term climate outcomes. Looking at 1 year or 5 years, we all know that's too short a period, that the short-term variations outweigh any longer-term climate effects. But what's nice about the underlying models is we actually have 150-year-long model if we count both the retrospective and the prospective runs. And so I want to look at that for Calcutta.
Oh, that's very interesting. I'm from a place very near to Kolkata. I was born and brought up in a place, Kharagpur, which is like 2 hours from Kolkata. And I grew up there, and I know that place is becoming so polluted over the last 3 decades. So this is extremely interesting place to look at.
Interesting. Okay, so this will be well, I'm not gonna spoil Sangram's day quite yet.
Yeah.
So this will be interesting to look at. So I picked the same model here again, the GFDL model from NOAA, and I picked. You see now I've picked the time range all the way from 1950 to 2100. Again, I'm going to look at max temperature. So, by the way, I've done a blog post on my personal blog at infolace.com/blog that does precipitation for the Tuolumne Valley, which is where Tuolumne watershed, which is where San Francisco's water comes from. So if you want to see an example with precipitation, I've used temperature here in all these examples, but if you want to see an example of precipitation, go there and take a look at it, and you'll see how we can work with precipitation, and that includes some important formulas for working with precipitation. But here I'm using temperature again because it's something that's all easy for us to get our heads around. And I'm comparing the two scenarios we have with GDDP, the RCP 4.5 and RCP 8.5. These scenarios, if you go to the documentation for our tool, the Climate Data Access tool that I'm showing you here, if you go to the documentation for it, we have links to papers that explain what these different scenarios are. And yeah, so Sangram is showing me an awesome sentence, which I've read but not ever remembered, from one of these papers. And it says, these scenarios are named after a possible range of radiative forcing values in the year 2100 relative to pre-industrial values, plus 2.6, plus 4.5, plus 7, 6.0, and plus 8.5 watts per meter squared, respectively. So some of you might grasp that in your head. Otherwise, go read the paper and understand. The important thing to understand about these scenarios is the high-end scenarios, RCP 8.5, as compared to the low-end scenarios, represent typically greater carbon emissions and worse land use choices. And I use worse pejoratively here, but land use choices that are biased away from forest cover. So you can read all about the details of that. We won't go into that here except to compare them. We expect RCP 4.5 represents a more aggressive intervention in terms of policy than RCP 8.5 does. Okay, so now we've talked about that. I've got this permalink here already, and oops, and of course if I click on it too aggressively, that's what I want. I'm just going to copy that. Now what I've done is I've done something a little bit different here. I've set up, using a tool called Docker Compose, a group of Docker containers, one of which is an OpenNext container. And I'll actually show, for those who get excited about Docker stuff, I'm going to show you this. This shows three containers running. One is an OpenNext access container. I use that container to look at any data set I choose in the OpenNext interface. And then I have an RStudio server, so I can run RStudio on the web, and a Jupyter server, so I can run Python in the web. And that comes with a bunch of, that server comes with a bunch of stuff installed, like NumPy and SciPy and Pandas, that for you Python programmers, you'll understand are the tools that you want to be able to work with this data. You can, of course, take this file and modify it to be whatever you want. This is a great resource, for instance, for doing classes, where you can set up a bunch of these servers running and have different students have their own server. I'm running this in Amazon EC2. That's nice because it's close to the data. Looking at 150 years of data across 2 scenarios, it's going to be a real amount of data. So why don't we dive in and look? I've thrown a tunnel through to this. How you access it depends on your network interface and some other things. I think I've set it up in remote. We might have to kick this a little bit. Hang on one sec. Let me make sure if this is still running. Try again. This is, of course, the weakness of doing a real live webinar where we haven't recorded anything is sometimes we have to deal with the networking glitches. Let's also make sure that my container is still running. Oh, here we go. Nope. Nope. I mean, it can't be reached. We have the port running, and let's make sure we have the container running. I'm going to restart it just to be sure. So this is Docker Compose running. I'm shutting down the Docker Compose. Starting it is really easy. You just say Docker Compose up. And then we should be able to connect to it on port 80. Yep, and here we go. So I don't know what was going on there. So now I have a set of files I've made. Some of these are R and some of these are Python. I'm going to look at this Jupyter notebook, which is a Python notebook that describes what we're doing. And what we can see here is we have a bunch of Python. I don't, not incredibly well documented, but let's actually clear the outputs so we get a fresh run. And let's do this. So now we're just going to load pandas and URL lists. We can do the data manipulation. And this actually runs pretty quickly. We define how we want to use matplotlib. Now again, we have a function to load the data, and we have a function to do graphing. The function to load the data again has read CSV at its core. Everyone has a function that says read CSV, and we can call that from where we're going. I'm sorry, this is the wrong file. That's why it's wrong. Hang on, let's go back here and pick the right file. Uh-oh, now I'm confused. Go ahead and figure it out. Oh, this is the one I want. Sorry, guys. I've done this so many times in so many different ways that I have different things for each one. Okay, so this is actually a better file. So let's run this file. Again, the fun of, so the same thing for the first two things. Oops. And now we have the function to load the data. This is the incantation. Docker lets me talk to the OpenNext container, the processing container I started, just with the name OpenNext. And then I can use my UID right here, the permalink I got when I was making the site that I copied before. And we see, again, it's very similar. We turn the date into a Python date type here, and we turn the temperature into degrees Celsius. I'm not going to convert it to Fahrenheit here because we're talking about Kolkata, which is part of the regular world that uses Celsius. And everyone, all my friends here who weren't born in the United States are laughing behind me. So let's load that, and then we'll load the data. I change this to be, is it still in there? Yeah, so this was the permalink I copied from the other page. It's a short thing, and I'm going to run this. This will take about a minute, and we'll talk about how things work when I do this. Let's start that. If we go over and we look in the Docker Compose window, sorry, wrong window, we can see it downloading and processing files. This is on our EC2 server. It's running very fast. You can see how fast the files are going by here, or you will when it catches up. I'm pushing the lag of this Hangout faster than it wants to go. But now we see the runs going by, and that will take a minute or so while we run. Get back to okay, so now when this loads, we'll be able to look at the data, and I'm going to pre-run this, so it'll just load us up. And these are similar to the functions we looked at in R. They'll tell us about what the data is going to look like in terms of rows and the contents of rows. So as soon as this finishes running and loading our data, we'll be able to see that. And then I'm also going to, and then we're going to use a function to graph it. Here we're going to look at a longitudinal graph over that period and compare the two scenarios. So I set the colors to be black for historical and green for RCP 4.5, and red for RCP 8.5. I do a bunch of work with pandas. If you haven't used, if you're a Python programmer who's working in the sciences and you haven't used pandas, it's a layer that works closely with NumPy and lets us do good sort of table management of data frames. Okay, here we see the data come in. We've got 500,000 rows here, and 8 variables in each row. We can see some of the different values. This turns out to be, we use GDDP here because it's global. It's not in the continental U.S. Quarter-degree resolution. We see we ended up with a 2 by 2 matrix of data. We have the 3 values for longitude and the 2 values for latitude. That defines our grid. And we see the 3 scenarios here, the 1 variable, the value, which is the temperature Kelvin, and the temperature now converted to Celsius. So let's set up this graph and look at it. So oops, sorry, I'm still programming in R here. Don't do that. Don't do that. This is the problem when you switch languages. And now we see, let's run this graph. So we're gonna run this graph now. This is run, and it compares the temperature, and this is the graph when it catches up that I think Sangram probably didn't want to see for his hometown. We see that this model shows a warming. We see on the left here that the temperature goes around 36 degrees Celsius, which those of us who live in San Francisco would think is way too warm already, to the daily high temperature. And then over the next 80 years, it climbs up into the sort of 38, 39. So it's a warming of 2 to 3 degrees. We could do some real modeling on this and get sort of what the means look like and what the trend line looks like, but I'm not going to do that in this demo. You Python programmers can do that, and we can do the same thing in R or MATLAB or other environments that you can work on. If you're skilled enough with Excel, you could even do this in Excel with pivot tables and statistical functions. And so that ends the demo I was going to give. I think using these tools, you can probably now go out and do a bunch of your own work and understand how easy it is to do. Again, if you want to use NetCDF or do other ways of working with this, go see the documentation. The mechanisms are pretty similar, but they're a little more complicated because NetCDF is more complex. And if anyone has any questions, we're getting to the end of our hour, but I'd be happy to answer any questions that people have. Just throw them in the chat or tweet them at us.
We got a hashtag in the chat.
Oh, Ilya posted the tweet hashtag. So if you want to tweet about this. Also, if you want to share this with colleagues who might be working on this, the URL for the YouTube that you came to, for the YouTube URL that you came to come to the webinar, That's going to be shared. That's going to be up, and and you can look at the recording there whenever you want. So if you want to come back and review a specific part of this because you actually want to dig in and use it, and I hope you do. We did this so that everybody can play with the climate data on their own, and because of the way we built it, it's actually free, so that's pretty cool. We're using free data on the back end, and then you do your own processing, so we don't need to spin up a processor for you. So please go ahead and use it, and share it with colleagues that you think want to look at this data.
That's kind of like feed here. So
Oh,
you can say hi backstage.
So, Ilya, do we have some questions, or is everyone absorbing this silently?
Yeah, I think it's more content, so people have questions probably, but we got no questions so far on Twitter or YouTube chat. So yeah, let's keep and your hashtags, Twitter, and see what's coming out.
Right. Okay.
So first,
there's a question here from James Gallagher.
Yes, James asked a question of, are we reading data from OpenDAP servers? Yes and no is the answer to your question, James. The data that we use by default to process this is the OpenNext data that's stored in S3. But there's an option to the script to alternatively pull data from the OpenDAP servers. We've retile data in S3, so it's in smaller tiles. So the S3 data, believe it or not, is actually more performant than the OpenDAP server in most cases. On the other side, we don't build an OpenDAP server for your data into our container. We let you download a NetCDF. So for those who don't know, OpenDAP is a way of serving NetCDF data that lets you do programmatic selection, and has a bunch of the same data also up in OpenDAP. If you look in the documentation, there's a chart about which data is in OpenDAP, but it's most of the same data as in OpenDAP that's in S3, and there are instructions in the documentation about how to go against the OpenDAP server. Generally, I don't recommend that because it doesn't get you much, and it's a little more complicated to get the tool to set up against it. If you care about it, in our comparisons, I think I mentioned in the documentation a little bit of the differences, but it's mostly the same data. Good question, James.
Let's wait a couple minutes. Maybe there are some other questions coming up. Maybe you could just talk a little about use cases where these models are useful.
Yeah, that's a great question. Where would people use these models, and how would we use it? And so there are three use cases that really excite me. One is people who are looking at risk analysis. And these especially include, for example, county planners, people doing insurance work, other people who want to understand really what are climate scientists and different climate models saying about the place where I live, where I work, where I write insurance, where I need to make emergency plans. So it's now easy to look at these different climate models and pull out data, as you saw for Calcutta, as you saw for San Francisco regional climates. Look at the Tuolumne thing I did, which is at infolace.com/blog, and it's right on the list there, for information about how to do precipitation. And you can look at the future of your area in that. And so that's a super exciting use case to me. And then two other use cases that are interesting to me are people who want to teach students about climate and the impacts of climate and how to work with climate data. The ability to set up an easy classroom environment, like I showed you with the Docker Compose stuff and the Jupyter notebooks. You can do the same thing with RStudio if you're teaching your class in R. That lets your students get hands-on with the data and work with the data themselves. Lets you set up problem sets in the form of a Python notebook or in the form of an R file. these are pretty powerful, right? So you can get users switching around and doing things. And we've used this for some classes that we've taught in Europe. Our head climate meteorology guy, Andres, has used it to teach classes with his students at the University of Tartu, for instance. And I think that's a very, very powerful way to use this. And then the third real use case that excites me is data journalism. We see a world where there's a lot of stories coming out about climate, but it's hard for journalists, even journalists who are data aware, to get good information about what the models are saying and to be able to work directly with those models. And so we think this tool is a real helpful tool that will let data journalists work with tools that they're familiar with, again, R, Python, MATLAB, Excel, and get data from models that leading institutions around the world have created and understand those models and put those models into their stories. So those are our three big use cases that come to mind for me.
Okay, we got another question here. Is one the distinction between the two data sets that GDDP has higher temporal resolution and DCP30 has higher spatial resolution?
That's exactly right. GDDP, I mean, first of all, GDDP is global, so you can look at places all over the world. So if you're outside the continental United States, that's the one you need to choose. But the temporal resolution is high, and it shows, I mean, obviously climate data is different than weather forecasting data in the sense the predictions aren't meant to really be what's July 7th, 2032 look like. But what it does tell you is what are the sort of local variations in time look like. And that's very doing things like drought prediction and other things. So you can get those kind of short-term variations and get what the models are telling you about that. For example, if you want to look at what do the models say about severe rainfall incidents, that's going to be much better from GDDP, which shows that daily resolution. You can see the spikes that the models are generating there. The DCP30 data at 800-meter resolution, and you saw this in the Bay Area, can give you information about microclimates. And of course, here in the Bay Area, we have 1 billion microclimates. So that data is, that's why I use that for Bay Area data. It doesn't give you the daily resolution. It only gives you monthly resolution. So it's very powerful there. It would be nice if you could dial either way, but the data requirements are extreme. Sangram, did you?
Yeah, I just wanted to add into really pictograms, right? That's just wanted to add into that question is if you have a really big compute facility, you could actually start running all those climate models, getting the outputs, and then implement something like a bias corrected spatial disaggregation BCSD downscaling methodology to create these global data sets at even higher resolution. The only reason why GDDP was at that 25 kilometer by 25 kilometer resolution grid was because of the fact that this actually takes a lot of computing. And even if we are sitting next to the supercomputer, it still takes a lot of time. So I think in the future, NEX, we are going to release a lot of other data sets, even higher resolution for global downscale data. I think this is a good start. And with the tools that you guys are building, you could easily ingest these other data sets as and when they come in, right?
Yep.
Making it so much easier.
Yeah, these tools are very general purpose that we built, and we're pretty excited. I mean, we have at Planet OS, we have a real commitment to helping the world understand our climate future in a lot more detail and being a conduit between scientists doing research in the field and the general public. And this tool is part of that commitment.
I think there's a follow-up question, just short, if you have time, Ilya.
Yeah.
I think it's an example use case for GDDP would be, say, adaptation information of seasonality for rural farmers. I think, yeah, I mean, I still did not get that question right, but I could see it's talking about probably vegetation seasonality or climate seasonality. I mean, there are a number of things. What was coming into my mind was global downscale climate data sets are so important. I come from a research background. I mean, we use these climate data sets to actually drive and constrain a lot of other ecological models, right? So when we are trying to let's say, for an example, I'm trying to see the resiliency of boreal forests, when climate actually changes, right? So with more warming, you could have more fertilization, and the trees are actually growing greener, right? I mean, so these are great things to look at, and now it'll be much easier to look at these things, right?
Right. I was just at Ohio State on Monday talking to agriculture group about just these issues about this tool and other tools. We need to distinguish again between climate models, which give us longer term models of how things will work, and forecasting models, which are better for, say, in season thinking. Planet OS does provide forecasting models for different channels. You can go to data.planetos.com, and we have, for example, NOAA's GFS models and a bunch of other good forecasting models for doing sort of nearer term, more forecasting work. For example, in-season farmer decisions. But for longer term planning and thinking about impact, certainly this is huge in agricultural regions. Thanks for the question. That's a great question.
Yeah.
So there is another one about like what would be some data sets that would be useful for comparing to the climate models. Like maybe there are some analytical cases where we can use different data sets in combination with climate models to build some answers, maybe find some artifacts.
Right. Certainly. One thing to do is compare with topological data sets, right? What is the actual land structure? And land use data sets? What are people doing with land, especially historically? The RCP data sets have some underlying assumptions about land use that you can investigate. I don't know how much they've captured those into formal data sets, but they must be someplace. I haven't actually played with that data. So that data can come in. And then, of course, comparing what the models are saying to what's actually happening historically is interesting, as a way both of understanding how accurate the models are and understanding, ways in which unusual things, for example, in Antarctic ice cover, are affecting what the models have predicted. And models, of course, are continually evolving. The scientists around the world are looking at these models and looking at new things happening, and including new ideas from what's really happening, almost day to day in the climate in their models.
Right. And just to add to that, actually, I think there are a lot of papers that are coming out on ways to do sensitivity analysis, right, for these different projections, because the uncertainties go up, and there are reasons for that. But if we know specific details about what that region has been going through in terms of CO2 rise or in terms of land use changes, and one can be ambitious enough to go and look into the NCAR CSM models and then change the parameters that are associated with CO2 fertilization and things like land cover changes and other radiative forcings, and then read on the whole model to generate those outputs to reduce that uncertainty. But it's again pretty exhaustive work, and people are doing that, I think. So.
Right. This tool gives you a great way to sort of follow along with, what the state of the art in climate change research is, and how these models are running without actually having to buy your own supercomputer facility, which I don't know. My credit card doesn't have that kind of credit limit, so so I love I both love and hate playing with this tool because a lot of the answers aren't really the answers I wish I was seeing, but it makes me feel more connected.
We got another one from Barcelona, from John. So Tom, can you share the links to your blog post you mentioned during the presentation?
Can you?
I think I can't post the links because links are forbidden in the chat.
Do you remember? Links are.
There we go.
So why is it not?
You can do it from your laptop because you're a host.
Oh, because I'm the host.
Yeah.
Okay, so the link is infolace.com/blog. Let me see. I of course don't know how to use this webcasting tool.
No, chat.
Oh, there we go.
Okay, we will figure out how to share it later.
There it is.
There we go.
Okay. Okay, yeah, Annika helps.
Oh, thanks. Thanks, Annika. Luckily, people are listening who know how to work these tools better than I do. So that's my blog about Tuolumne. That shows the precipitation. And this is actually my favorite feature of Google Hangouts, is the infinite feedback loop. That makes me feel like I'm in an episode of Max Headroom or something. For those of you old enough to remember that. So yeah, please go there. And Annika, maybe you could post a link to the OpenNext site itself. And if you go down to the bottom of that page, there's documentation down there that shows you all how to use this with examples. And we've got a bunch of Python sample notebooks and a bunch of R sample code that you can use to run it. And if you have any questions, please reach out to us either by Twitter or by emailing one of us. You can email me at tom@planetos.com, and we'll help you use the tool, because we're real anxious to have people able to access their climate data from here. Sangram, do you have any parting words before we sign off?
The parting words would be, I think Planetos is doing a great job on making these tools available to the common public, and even for researchers like us, it's a very fast and efficient tool to see things if we are really producing the good data set. So I think.
And my old friend Chase Turner is asking if there's a Mathematica example before we sign off. Sorry, we haven't done a Mathematica example, but I bet you can based on what you saw today. So if you need any help, Chase, give me a shout.
All right.
Very good. Okay, have a great day, everyone.
Thank you.
Thanks a ton for joining us.
Yes. Okay, maybe one more time. Tom.
Oh,
here we go.
we're waving at the camera.
Yeah.